Hello there, my name is Ben and welcome to this math video tutorial on induction. We're doing proof by induction, and the topic for this proof by induction is divisibility. So we're going to look at how to prove statements with divisibility, I mean. Sorry about that. So let's say we have this statement. I'm going to prove that 3 to the n plus 1 is even. So we want to show that 3 to the n plus 1 is even, and this is true for any n in the set of the natural numbers. Okay, so the way we're going to do this proof is we're going to let our statement, let P of n be 3n plus 1 is even. And so then we're going to check that P of 1 is true. And so the way to do that is we're just going to let n equal 1, so we know 3 to the 1 plus 3 equals 3 plus 1 is 4. And, we can see that that's 2 times 2, so we know it's even. Okay, so we found out that P of 1 is true, so we check that off our list. And now we're going to assume P of k is, and we're going to say that statement is 3 to the k plus 1 is even. And so another way to say this is that 3 to the k plus 1 is equal to, let's say, 2m for some natural number m. And then let's prove P of k plus 1. So this will be our induction step, and we're going to kind of go outside the proof to do some scratch work here. So if we did 3 to the k plus 1, we know that that's equal to 2m for some natural number m. And if we do 3 to the k plus 1, and k plus 1, that's equal to 3 to the k times 3. And then we have plus our 1, just adding the 1 there. And we need to basically find something where we can get 3 to the k plus 1. We know if we factor out of 3, we can get 3 to the k, but we also need a plus 1 to get 3. So that means if we're going to add a 3, we need to subtract the 3 to make this statement unchanged. So if we do that, let's see what happens. So we're going to get 3 to the k plus 1 equals 3 to the k times 3 plus 1, and that's the same thing as 3 to the k times 3, and then we have plus 3 minus 3 plus 1. And we see that if we group this together and then these two numbers together, we're going to get 3 times 3 to the k plus 1 minus, and that's going to be 2 because negative 3 plus 1 is negative 2. And then if we just work down just a little bit below, we see that 3 to the k plus 1, we can replace that with 2m, right? Because we know that's even. So we have 3 times 2m minus 2. And that's going to be equal to, and then we can factor out 2 and see we get 2 times 3m minus 1. And so since we found that this is equal to 2 times 3m minus 1, we know that since m is a natural number, that 3m minus 1 also is a natural number. So 2 times anything natural number is going to give you even. So we know that this is true. So we know that this is even. So therefore, just putting this to the side, we know that P of n is true for all n for natural numbers. And then there's the proof. So we're done. So that's how we show that 3 to the n plus 1 is even using proof by induction. Okay, so that was one example. Let's look at another example. And we'll start on a new board here. For this one, we're going to say prove that 9 to the n minus 4 to the n is divisible by 5 for all n and n. So we're going to prove that 9 to the n minus 4 to the n is divisible by 5 for all n and n. So what that means is that we're going to show that 5 is going to divide that quantity, 9 to the n minus 4 to the n. That's what we want to show. So let's do that. We have proof. Okay. So we're going to let P of n be this statement. 5 divides 9 to the n minus 4 to the n. And we'll say for all n and n. And then we're going to check P of 1. So we're going to get 9 to the first power minus 4 to the first power. So that's 9 minus 4 equals 5. And that's the same thing as 5 times 1. So we know that P of 1 is true because that's divisible by 5. And now we're going to assume P of k, just replacing all the n's with a k, so 5 divides 9 to the k minus 4 to the k, so 5 divides that quantity. Let's say for all k in natural numbers. And now let's prove the P of k plus 1 case. So we're going to do some scratch work on the side over on the left here. And we'll do 9 to the k plus 1. We know that's equal to 9 to the k times 9. We know that 4 to the k plus 1 is equal to 4 to the k times 4. B of k plus 1, we need to make sure that we define this as 9 to the k minus 4 to the k. And we can say this is equal to 5, right? Since 5 divides it 5 times, let's say, some natural number t. So t is in the set of natural numbers. So that's our equation there. We're given 9 to the k minus 4 to the k. So if we have 9 to the k times 9 and then minus 4 to the k times 4, we know we need a 9 to the k minus 4. So if we factor out a 9 here, we're going to get 9 to the k. And I got to have a minus 4 to the k inside here to get that 5t. So that means I got to have a minus 9 4 to the k, and I also have to add a plus 9 4 to the k. So we'll see how that works in the induction step. So we're going to do that right here and right now. So we got 9 to the k plus 1 minus 4 to the k plus 1. So that's equal to 9 to the k times 9 minus 4 to the k times 4. So that's going to be equal to 9 to the k times 9. And then we're going to have minus 9 times 4 to the k plus 9 times 4 to the k. Because whatever we subtract, we also have to add. So this is like adding a 0 here, because anything negative plus adding to itself gives you 0. And then you're going to have your minus 4 to the k times 4. So when we do that, we get a factor, group these two together, and then group those two together. And so we're going to factor out a 9 here, so that's going to be 9 times 9 to the k minus 4 to the k. And then plus, we have a 4 to the k here, so we're going to factor out 4 to the k, and that's going to be 9 minus 4. So that's the same thing as 9 to the k minus 4 to the k. We assume that was 5t because that quantity is divisible by 5. So we have 9 times 5t plus 4k times 5. 9 minus 4 is 5. And then we factor out our 5. So we want to show it's divisible by 5, so 5 times 9t plus 4 to the k. And we can see that when t and k are natural numbers, that 9t plus 4k is also a natural number. And we know that 5 times a natural number, that shows it's divisible by 5. So we proved that the p of k plus 1 in the induction step, we see it's divisible by 5. So we can say, therefore, p of n is true. And then we can say for all n in the natural numbers. And then in our last proof, we forgot to put a symbol at the end indicating we're done. So you can put a little diamond here, colored in. It shows that we're done with the proof. Or use your favorite symbol, smiley face, or QED. You can stamp a QED to it and show you that you're done with the proof. So here, just want to make a quick note that all this stuff we did on the side here, this scratch work, we didn't include in the proof, because the mathematicians, the people that read the proofs, they don't really care about the details, how you got it. They just want to see the result. So you basically work out your scratch on the side here. This is kind of like side work. And then you use what you got in the side work to incorporate that in the proof. And that will show you why it's true. So you don't need to go through all the details of how this is equal to that, this is equal to that, and all that. This was kind of your scratch work on the side. So scratch work does not belong in the proof, but it does help you to get to why something's true. Gets to the truth of the matter. So anyways, it looks like we're done, with this video, proof by induction, talking about divisibility proofs. And again, my name is Ben. I want to thank you for watching this video. I hope you learned a lot from it, and stay tuned for watching more math videos on the math channel. And I hope you have a good day. Take care. Bye-bye.